The periodic table functions as the literal source code of the physical universe, an architectural map of the building blocks defining our reality. If we isolate just the second vertical column, the alkaline earth metals, we find a precise progression in atomic mass, starting at element 4 and descending down to element 88. Most people look at this group and think only of the calcium needed for skeletal health. But without these specific elements, the modern world would seize up. Space telescopes would lose their mirrors, structural engineering would lose vital alloys, pyrotechnics would lose their color, and hospitals would lose the ability to image internal tissues. Moving down this single vertical column reveals an escalating scale of atomic mass that dictates how our tools, our technology, and our biology operate. At the top sits beryllium, element 4. It holds a small nucleus with exactly 4 protons, surrounded by tightly bound electrons. This chart shows its weight to strength ratio. Because it's so tightly packed, the metal is exceptionally light, yet incredibly rigid. Engineers rely on that exact ratio to build the golden mirrors for modern space telescopes, allowing these massive structures to survive the violent forces of a rocket launch without collapsing under their own weight. Dropping further down the column, we add more protons and move to heavier elements, magnesium at 12 and calcium at 20. In heavy industry, magnesium burns with a dazzling white flame and is used to forge and strengthen modern metallic alloys. But inside the human body, calcium provides the rigid architecture for your skeleton, while both elements act as biological batteries, generating the electrical voltage required to power your muscles and maintain the rhythm of your heartbeat. Just a slight increase in protons shifts the column's utility, moving from the rigid materials used to explore the vacuum of space to the dynamic internal engines driving human life. Descending further, the atoms become heavier as we hit strontium at 38 and barium at 56. Because these larger atoms hold more complex electron structures, they release energy as highly specific wavelengths of light when heated. This specific physical reaction is what paints pyrotechnic displays with brilliant red and green light. Barium carries that high atomic density directly into medicine. Because its atoms are packed tightly enough to physically block X-rays, doctors use it to cast shadows of soft internal tissues that would otherwise be invisible on a medical scan. Finally, we reach the absolute bottom of the column, element 88, radium. Radium is unstable because its core is so massive and densely packed. To relieve that internal tension, it constantly bleeds off energy in the form of raw radiation. When researchers discovered how to harness that constant radiation output in the early 20th century, it created a completely new branch of medicine, laying the groundwork for modern radiation therapy and nuclear science. This density and instability at the base of Group 2 allow doctors to manipulate human cells and peer into the unseen realms of the body. This timeline summarizes the full vertical journey down Group 2, starting with a mere 4 protons and ending at 88. By packing in more mass and extra electron shells, an element's interaction with the physical universe entirely changes. We move from capturing starlight with ultralight metals to powering the electrical rhythm of a heartbeat, painting the night sky, and emitting pure nuclear energy. The next time you see a burst of color in a firework, look at a medical scan, or feel your own pulse, you are witnessing the specific, escalating mechanics of the alkaline earth metals at work.